So now let us start the proof of our uniqueness theorem. So really do the formal calculations. Yeah, and as I just hopefully convinced you, it is a good ansatz to define our hopefully projection operator in the following way. So I'm putting my operator P as WH, where H is this Gaussian kernel, so it's 1 over 2 pi integral over WST e to the minus 1/4 s squared plus t squared ds dt. And so I mean this function here together with the 2 pi, this is my h. So this is WH, for h is equal to 1 over 2 pi e to the minus 1/4 s squared plus t squared. Yeah, and now I'm claiming that this guy, this P, actually is an orthogonal projection. So that's the first thing which we have to see. The claim is P is an orthogonal projection. And what does it mean? I mean, orthogonal projection, of course, means this guy should project down onto a sub-Hilbert space in orthogonal way, but it's good to know that we can reformulate this in a very algebraic way, namely being an orthogonal projection on a Hilbert space is the same as algebraically saying that P squared is equal to P and it's self-adjoint. So P squared is equal to P is the projection property, and self-adjoint is that it's really an orthogonal projection. So what we really have to see is just algebraically that P star is equal to P and that P squared is equal to P. Just algebraic properties, and of course our operators, the W's, we know some algebraic properties of them, so there is some hope that we can do this without really looking into how those guys act on the Hilbert space. Yeah, and one is very easy now, because if we take the P star, then I mean all this here is real. So we only get the star here, and we know that the W's are unitary, and in particular the joint of this is just given by replacing s and t by minus s and minus t. So for one, we just have to write down that P star, so this is 1 over maybe, no, it's 1 over 2 pi, and then we have the integral, and here we get W of st star e to the minus 1 over 4 s squared plus t squared ds dt, and this here, as we know, is W of minus s and minus t. And now you see, because I have here s squared and t squared, it doesn't matter whether I have here s and t. So if I'm replacing here s by minus s and t by minus t, then you see that my integral is not going to change. So this means this here actually is equal to P. Because I have here, because the form which I have here, that this is really something in s squared and t squared, which doesn't see the minus sign. Yeah, okay, so it remains to see that P squared is equal to P. And for this, it's actually good, also for later purposes, to look on a more general calculation. So namely, so in order to show 2, it's good to calculate. So one calculates more generally what happens if I'm putting, instead of looking on P times P, I'm putting another W in between, and then check what I'm getting there. And what one gets is what I'm now calling part 3. Let's say that P W of xy times P, and I'm claiming that this reproduces P as it should up to some factor which depends of course on x and y, and this factor is very nice, namely it's e to the minus 1 over 4 x squared plus y squared. So it's just the kernel h from which I started times P, and this is true for all x and y real numbers. Yeah, good. Okay, and this is something which, again, this is straightforward, simple calculation by using the properties which I have for the product of two W's. I mean, because the P here contains W's and here, so I'm just multiplying here 3 W's, and for this I have formulas how to do this. And if you use this, I mean, you get this. I'm not going to check this, it's just straightforward, but of course it's without doing the calculation, maybe it's hard to guess what you get in the end. But if you do the calculation, you will just get it. So everybody should do this by themselves. And of course, this uses the properties in proposition 8.4, the product of two W's, which we had there. Yeah, and then of course, if I have this, then this is more general than this, because if I put here x and y equal to 0, then this here is the identity, and here of course this will be just 1, and then I get a p squared is equal to p. So then 2 follows if I'm putting x and y equal to 0. There we get p squared, which is the same as p w 0 0 times p. Okay, and because this is the identity, and according to this rule here, I will get here e to the, and here I have 0 squared plus 0 squared, so just a factor 1, so this is just p. Okay, so this is just a special case of this. Yeah. And so this tells us that really we have here a projection. In purely algebraic terms, from the Weyl relations, we have produced a projection. And now, of course, the idea is we should project with this projection. And what we get is more or less the space of our vacuum, or vacua. I mean, maybe we have more. It might not be a one-dimensional space if it's not irreducible. But of course, it's important to see that this space is not just 0. So that this projection here really projects down onto something non-trivial. And for this, we need this property, which we saw in the beginning, that the mapping H goes to WH is injective. Because the H which we are using here is, of course, this function here, which is non-zero. So this means this operator P is also non-zero. So it's now good that we check this at the beginning. So we have H is not 0, so this means that this operator P, which is the W of H, is not the 0 operator. So it's really a non-trivial projection, and this means it projects down onto a non-trivial subspace of our Hilbert space. Yeah, so thus, if I'm applying P to H, so I'm taking the range of this, so that's what I'm projecting onto. This is not just the 0 vector. Yeah, and then of course the idea is now this space here, this should now be the vacua. And so what we do is now we take an orthonormal basis of this space, and then we try to see how our representation behaves with respect to this. So what I'm going to do is I'm choosing an orthonormal basis. So this range of my projection is a closed linear subspace of the whole Hilbert space. So it's a Hilbert space of its own. So it has an orthonormal basis. And because everything is separable, this basis is at most countable. It might be infinite, so this space might be infinite, but it can only be countable. So I have an orthonormal basis, which I denote with omega n. And n is now running from little n to capital N, and capital N is the dimension of this space here. So it's either a finite number or it might be infinity. So this is an orthonormal basis of this range of P. So it's the space on which we are projecting, and so this n here is either a natural number, or if this subspace is infinite dimensional, then it's infinity. And then I have here an infinite basis. Okay, and now, of course, the idea is now that those omega n's here, they decompose somehow my representation into irreducible parts. So in particular, what happens if I'm acting with the W's on the omega n? I should not be able to make connections between different of them. So what I'm doing here is now I'm putting for each of the n's, which shows up here, so for n, little n from 1 to capital N, I'm saying Hn is by definition the span of my operators Wst acting on omega n for all S and T in R. Okay, and so I'm taking the span, but I'm also taking the closure. So everything which I can approximate by acting with arbitrary of those Wst on those guys. And of course, because we know that if I'm multiplying two W's, I'm just getting another W. So it's clear that I don't have to take products here. It's enough to take just one of those guys. Yeah, and now the idea is that my whole Hilbert space decomposes into a direct sum of those guys, and my representation also decomposes with respect to this. So my representation of the Weyl relations should be a direct sum for the representations acting on those Hn. So each Hn, on each Hn, I should have an irreducible representation. And so what we have to check is that indeed this is true. We have this direct sum decomposition, and then we have to understand how does this irreducible representation on each of the Hn acts. And of course it should be the Schrödinger representation. But so we still have to see a couple of things.